In these notes, we're going to compare some information about zero, first, and second order rate reactions to each other. These are the three that you're most likely to need to know the most detail about when it comes to the AP test. So the first thing that I have is just the definition of the rate law. So we know that a rate law is equal to the rate law constant times the concentration to a certain exponent. So for zero order, the rate law, the exponent on the concentration is 0. Or in other words, it's just the rate is equal to a constant value. For first order, the rate is equal to the rate law constant times the concentration of a reactant to the first power. And for a second order reaction, the rate of the reaction is equal to the concentration of a reactant raised to the second power. So if you do some calculus, you can get what's called the integrated rate law. We don't need to worry about how you get from A to B. And the integrated rate laws will be on the AP sheet. They don't label them as zero or first order or second order, but they are all there. So if you know how to tell them apart, you don't need to memorize them. For a zero order reaction, the concentration of reactant A at the end of a reaction, or at some end of time, is equal to negative times the rate law constant times time plus the initial concentration of A. So you don't need to memorize this again. It's on the AP sheet. The purpose of the integrated rate law is that it allows you, like if you know the starting concentration, you know the rate law constant, you can figure out the concentration of the reactant at some other later point in time. It also makes it a little bit easier to deal with or to interpret a graph of the rate law. So it kind of puts this into a format you should be used to from physics, y equals mx plus b. So if we want to think about what a graph would look like of concentration versus time, if we put the concentration on the y-axis and time on the x-axis, because this is zero order, the rate does not depend on the concentration of the reactant. The rate is constant. So making a concentration versus time graph would give you a linear graph. The slope of that graph would be, just like here, negative k. And the y-intercept of the graph, which is right here, would be the initial concentration of the reactant, which kind of makes some sense. I should put the units there, would be molarity. Next, oh, and then the half-life. And we should probably define what half-life is first, because this is the first time that it comes up. Half-life is the time that it takes for the concentration of the reactant to be cut in half as compared to the initial concentration. And you can figure out this half-life equation by going back to the integrated rate law and making the A final equal to half the A initial. If you know the rate law constant, then you could solve for time. That's really all that's done, but these are often given as separate equations just to save you a little algebra. So the half-life time for a zero order reaction is equal to the initial concentration at the beginning of the time interval divided by 2k. That is not on the AP sheet. So they're not usually going to ask you questions about it, but since the integrated rate law is in there, you could conceivably be expected to figure it out. All right, moving on to first order. So first order reaction, the rate is dependent on the concentration. The integrated rate law, again, is on the AP sheet. And for a first order reaction, the natural logarithm of the final concentration of the reactant is equal to negative kT plus the natural logarithm of the initial concentration of the reactant. So for this, a linearized graph, this is actually what we saw happen, the kind of graph that we got in our crystal violet lab. So we saw that to linearize our graph of concentration versus time, we had to take the natural logarithm of the concentration to get a line for our graph. The initial, or the y-intercept, is the natural logarithm of the initial concentration of A, and the slope of this graph is equal to negative k. And you can really figure that out by looking at the equation. Again, y, well, on the y-axis we have ln of A equals mx, so the slope is negative k, time is on the x-axis, plus b, so the y-intercept is equal to the natural logarithm of the initial concentration of A. Again, you can figure out the half-life by using the integrated rate law and substituting in like half of the initial concentration for the final concentration, then rearranging to solve for t. And it turns out for this, you get 0.693 over k. It is important to note here, first, that this is on the AP sheet. And second, and interestingly, the half-life, which we write as T1/2, is not dependent on concentration. And it's also important to notice it's constant. So no matter how much reactant you start with, if something is a first order reaction with respect to a reactant, the half-life is not dependent on the concentration that you start with. So if you start with 10 molar of something and the half-life is 60 seconds, in 60 seconds the concentration will go from 10 to 5. If another 60 seconds pass, the concentration will go from 5 to 2.5. If another 60 seconds passes, the concentration will go from 2.5 to 1.75. So even as the concentration changes, the half-life actually stays the same. The third order of reaction that you need to know about is second order. So this one, it is again on the AP sheet, but you need to be able to recognize it. The integrated rate law is 1 over the concentration of the reactant at the end is equal to positive kT plus 1 over the concentration of the reactant at the beginning of the reaction. For this one, if we were to see a second order reaction take place, we would linearize the graph of concentration versus time by doing the reciprocal of the concentration. That would give us a linear graph that would look something like this. The slope of the graph this time, again, y equals mx plus b with this equation is how we can connect the equation to the graph. So on the y-axis, we have 1 over the concentration at any point in time. The slope is going to be equal to k, the rate law constant, and the y-intercept is going to be equal to the reciprocal of the initial concentration. So if I put a dot here, this would be 1 over the concentration of A at the beginning of the reaction. So to summarize what you need to know, you don't need to memorize these three reactions, but you need to know that a zero order reaction is just kind of plain. The regular graph, concentration versus time, is linear. If you have a first order reaction, you need to be able to recognize the rate law from the AP sheet, and you need to know that a graph of the natural logarithm of A versus time will be a straight line. And for the second order rate law, you need to recognize the integrated rate law. You need to know that the graph will be a straight line if you plot the reciprocal of concentration versus time. When I almost forgot to put the half-life equation for this one, half-life would be equal to 1 over K times the initial concentration of A, and this one's not on the AP sheet. But I, again, just want to point out to you the important thing you want to know about half-life is, of these three half-life equations, only one of them's on the AP sheet, but also that one is the only one that does not depend on the initial concentration of A. So the half-life is constant. That means if you're looking at half-life data and every same amount of time the concentration is cut in half, that's going to be a first order reaction. It also means that if you know the half-life, you can figure out the rate law constant. Or if you know the rate law constant, you can figure out the half-life. So this is a great summary to have in your notebook and reference as you are practicing your homework. Also work on understanding how to connect those integrated rate laws to what you need to know about the graphs, because that will not be on the AP reference sheet.